Robots are changing the world, with vast potential to transform many industries and businesses. In a recent report by the McKinsey Global Institute, advanced robotics has been identified as a key disruptive technology, bringing $6 trillion in economic value to manufacturing and $3 trillion to medicine in the coming 10 years. For robots to reach their full potential in helping us with our dull, dirty, and dangerous work, however, there still exist some challenges. Right now, robots heavily rely on pre-programmed behaviors to complete tasks, often in very constrained environments. This creates significant bottlenecks when coding each unique robot for each unique task. A new robot behavior may take months to years with multiple expertise to implement. Yet, in the fast-changing environments of today, and even more so of the future, robots will need to adapt to our increasing demands and leave the comforts of the lab. With the birth of cloud technology and ever-enhancing robotic hardware, a new field of robotics has surfaced: shared knowledge robotics. Goldburn and Kehoe from Berkeley defined this as a new approach to programming robots. It takes advantage of mass knowledge platforms to achieve massively parallel computation and real-time sharing of vast data resources. Inspired by the way people learn new skills from one another, my work focused on a particular kind of shared knowledge robotics, where robots can peer learn. This platform typically has 3 layers: the databases, the cloud engine, and the robotic clients. The databases are the primary layer that stores all the software elements, from your basic objects and maps to simple action recipes that show basic movements such as to move or to scan. The cloud engine then combines these software elements into generic software components, similar to a more complicated but generic action recipe. So in move to door, this would tie in the basic recipe of move to the object door. The robots themselves then would translate and filter through these generic software components to suit each robot's specific hardware. This is done through a hardware abstraction layer. That could be a couple of low-level drivers. So in the example of move to door, the PR2 would know to use its wheels to move to the door, whereas the now robot would know it should use its legs and balancing mechanism instead. Cloud technology is also very critical throughout the whole system and allows users to externally access data through its networks. Knowledge is transferred both ways. What that means is knowledge from one robot can in turn update the databases and help robots on the other end get the most current data to perform their existing or coming tasks. So this more or less resembles remote or peer learning amongst robots. To ease the burden on developers and introduce engineers to a broader range of complex programming, I designed a novel interactive graphics user interface, or GUI, to help skill transfer between robots. As a proof of concept, I created a number of action recipes using the robot's left arm movement. They can be stored and replayed on multiple robotic platforms, such as the PR2 and the Now robot. We would first initialize the system's main and supporting software, and then the robots themselves and the bridging software as well. Users are then able to form, play, and store the routines. Finally, by modifying some of the existing code, the user can then use the same GUI to transfer the task recipe to another robot and have it executed as well. Let's have a look at a recorded demonstration. Here, an action recipe depicting an ushering movement is formed using standard skills termed point up, point down, and point up. We can now see that the task recipe is being executed on the PR2. This ushering task recipe will then be transferred to the Now robot, as shown here. Guiding through the creation of this GUI are a number of design tools, choices, and concepts. The most important of all is the Python programming language, used throughout the design, flexible, usable without compilers, and relatively quick. Python is the most preferred language after much decision. Pyride, or Python-based robot interactive development environment, is the software middleware that supported the rapid interactive development of robot skills and behavior. It itself is a software package on ROS, or the Robot Operating System, an open-source framework for developing robot applications. Here is a breakdown of Pyride, which I used to develop my system. It has a client-server model and can communicate with Telnet, as well as tie in low-level software packages that contain robotic functions as nodes. In other words, it is an integrator, and I can easily control any robot that has Pyride installed. My first prototype was made using Tatinker, the inbuilt GUI designer within standard Python libraries. I used this prototype to test and evaluate desirable functionalities by gaining feedback from potential users. With this, I undertook an evaluation of more comprehensive GUI design tools. I found two: the Qt project and its cousin, Python PyQt4, and the web developer, Django. I chose PyQt4 in the end because of its more sophisticated widgets, and that it itself is enough to make a powerful and fully functional prototype within the timeline of the Capstone project. The system is also tested on the PR2 and Now robot. These robots were selected because of their difference in hardware and the difference in degrees of freedoms in their arms. My system then had to accommodate for their similarities and differences during the skill transfer from one robot arm to another. The PR2 is one of the most widely experimented robotic platforms in the world. 34 institutions, including Bosch, where I previously interned, and Universität Stuttgart, where I previously exchanged, also has one. The one at UTS is also the only one in Australia. A major factor in choosing this platform is because my system can be immediately shared with these online communities. The Now robot is a humanoid robot developed by Aldebaran Robotics. Chosen to be a human companion and an educational tool, it is also a standard platform in the RoboCup Standard Platform League. It too, like PR2, has an online community where I can share my system. Elements of human-computer interaction, learnability, flexibility, and robustness are also repeatedly considered throughout the design. Features like voice prompts, loading pre-made routines, and input checks were considered to let users familiarize with my GUI and help them achieve maximal outcomes. A key feature of my work is that it is extendable. In other words, I can add reasoning and adaptive capabilities to my GUI. This could be achieved by integrating knowledge processing systems like NoRob into it, so as to help robots link up different knowledge and help them make smarter decisions and help them step towards artificial intelligence. I would say that my system acts as an entry tool towards the research field of shared knowledge robotics. It ties in with other disruptive technologies as well, such as the Internet of Things, and provides online development communities more resources to fuel their research. The project also gathered insight from the Sydney Python group and built upon the work of existing expertise within the Magic Lab. Pyride is also developed by the lab, and thus has helped it towards its open source release. The project also represented UTS as part of an entry to the 2014 International Conference for Social Robotics, and in its competition earned third prize for displaying an idea that serves as a significant improvement to human life quality. In fact, we can see that the nature of work is radically changing, and changing quickly, such as in manufacturing and medicine. This means that my project is responding to a pressing social phenomenon, which would deliver significant comparative advantage in economic reform on products and services for this country in the future by helping to make robots in the workplace and reality. I welcome the audience for any questions. Thank you.